Assalamualaikum warahmatullahi ta'ala wabarakatuh, and very good day to everyone. Okay, so basically today we continue from last session of fundamental of thermodynamics. Okay, so basically today we focus on second law of thermodynamics part 2, which is Carnot cycle. As in part 1 we have discussed on the heat engine, so today we focus on Carnot cycle. Okay, so refrigerator and heat pump. So a refrigerator and heat pumps is a machine or device that move heat from one location to another location using mechanical work, that convert work to heat, or heat engine operating in reverse. So basically, as we know, the heat will transfer from hotter place to a more colder place. So basically, heat pump and refrigerator is going to remove heat from a lower temperature to a hotter temperature with the additional of mechanical work. So that we call it as a refrigerator and heat pump. So a refrigerator and heat pump is a machine or device that move heat from lower temperature source to a higher temperature source using mechanical. So basically, note that, look at these notes. In nature, heat transfer from high temperature medium to low temperature 1 without requiring any devices. That we call it as a nature. In natural, normally we can see or we can feel that the higher temperature will transfer heat to a lower temperature. So at the end of the day, it will be stabilized, or we call it as a equilibrium condition. And refrigerator is used to maintain the refrigerated space at a low temperature by removing heat from it. And heat pump is used to maintain heated space at a higher temperature. So normally refrigerator at our house, so we can find it at kitchen. And heat pump, normally in Malaysia we use aircon to cool down the space, but in a winter country they need a heat pump in order to hotter the space. So this is the basic mechanism of refrigerator and heat pump. So we have a condenser here, which is the heat being transferred. Okay, that is the higher side, Q hot. This is your compressor, and the compressor need a work, electrical work, something like that, a power device to compress the fluid. Okay, so this means that compressor use a work. And this is a refrigerator, this is the evaporator, whereby it absorbs heat from a refrigerated space. And this is a expansion valve. So we will discuss this further in the next section. Coefficient of performance. So basically, the efficiency of refrigerator and heat pump is expressed in terms of coefficient of performance, because COP, or coefficient of performance, is more than 1. Normally is more than 1, whereby efficiency normally is below than 1, whereby you got 1 for efficiency is 100%, but for COP you can get more than 1, and below than 1 you have a problem. Okay, so refrigerator, the objective of refrigerator is to remove heat, Q low, from a refrigerated space. So this is your warm environment, this is your low environment. So in the middle you have a work net required to refrigerate. Okay, so heat being transferred to warm environment and heat being absorbed So this is your desired output. This is your required input, because you want the heat being absorbed from your refrigerated space. So normally this output we put at the top side, divided by your work. So how much output you required per your work net in. So from this equation you can get your COP, coefficient of performance. And then you can rearrange. Work net is Q hot minus Q low. So you can substitute this equation into this equation. You got this equation. Okay, whereby for heat pump, alright, so heat pump is like similar with refrigerator, but the desired output is your Q hot, because you want to warm up the space. Okay, for refrigerator you want to cool down the space. So heat pump, you want to warm up the space. So the Q hot is your required output, whereby your input is your work net. So the output we take at top divided by work net. Okay, so the COP will be something like this, or COP for heat pump is equal to COP of refrigerator plus 1. Alright. Okay. Second law of thermodynamics, Clausius statement. It is impossible to construct a device that operates in a cycle and produce no effect other than the transfer of heat from a lower temperature body to a higher temperature body. So it states that a refrigerator cannot operate unless its compressor is driven by an external power source, such as electrical motor. So which means that this operation requires work in, such as motor powered by electric. So this way, the net effect of the surrounding involves the consumption of energy in the form of work, in addition to the transfer of heat from a colder body to a warmer one. To date, no experiment has been conducted that contradicts the second law, and this should be taken as sufficient proof of its validity. So basically, there is no, if you want some heat engine from a colder to warmer without additional heat, additional work, it will contradict with Clausius statement. Okay, so a refrigerator that violates the Clausius statement of the second law. So this is violates the Clausius statement. Equivalent of the two statements, Kelvin-Planck and Clausius statement. The Kelvin-Planck and the Clausius statement are equivalent in their consequences, and either statement can be used as the expression of the second law of thermodynamics. Any device that violates the Kelvin-Planck statement also violates the Clausius statement, and vice versa. So basically, Kelvin-Planck heat engine cannot convert all heat into work without leaving part of it into the surrounding. So whereby refrigerator and heat pump need external power to move heat from low to high temperature. So this is a difference between Kelvin-Planck and Clausius statement. So basically, no device currently, I don't know in the future, but currently no device violates this statement. Sample problem 4.4. Sample problem 4.4. The food compartment of a refrigerator is maintained at 4 degrees Celsius by removing heat from it at a rate of 360 kilojoule per minute. If the required power input to the refrigerator is 2 kilowatt, determine A. the coefficient of performance of the refrigerator, and B. the rate of heat rejection to the room that houses the refrigerator. Okay. 4.4. Okay, so given directly, the food compartment is to maintain 4 degrees Celsius. Okay, and the rate of heat being rejected, so heat being rejected, Q, as is a refrigerator, normally the lower part is the heat required, because we absorb the heat and release it in the environment. So basically the heat given is 360 kilojoule per minute. Alright, so basically this is a minutes. For kilowatt, watt is joule per second. So you need to convert into kilojoule per second. Okay, so thus, or we have a kilowatt. So need to convert first into the second. Okay, alright, and the power input work net power input, that is the total power. So work net is 2 kilowatt. Okay, so A, coefficient of performance, COP, refrigerator. So we have Q dot over work net. So here, okay, we got 360 kilojoule per minute. Okay, so you need to convert into second. So 1 minute 60 second divided by 2 kilowatt. Okay, so you got your coefficient of performance, COP. Okay, so B, rate of heat rejection. Okay, so here is the rejected to the environment is your Q hot. Okay, so work net is Q hot, Q low. So we got so rearrange the equation. So Q hot work net minus Q low. Okay, so in kilowatt we have Q low, and also we have Q net, work net. So you got your QH, okay, in kilowatt. Okay, all right, thank you. Sample problem 4.5. Sample problem 4.5. A heat pump is used to meet the heating requirement of a house and maintain it at 20 degrees Celsius. On a day when the outdoor air temperature drops to -2 degrees Celsius, the house is estimated to lose heat at a rate of 80,000 kilojoule per hour. If the heat pump under this condition has a COP horsepower of 2.5, okay, determine A, the power consumed by the heat pump, and B, the rate at which heat is absorbed from the cold outdoor air. Okay, so 4.5. Okay, so given directly, temperature inside the in is 20 degrees C, and the out is minus 2 degrees Celsius given directly. Okay, and also the heat loss rejected to the environment is your Q hot is 80,000 kilojoule per hour. Okay, so here is a per hour, so you need to convert into kilojoule per second or kilowatt. Joule per second is watt. Okay, so you need to convert this. And given the COP, this is a heat pump. COP heat pump is 2.5. Okay, so that is the data given by the question. So A, power consumed by the pump. Okay, consumed by heat pump. Work net. Okay, alright, so work net, sorry, COP heat pump is Q hot over work net. Alright, so we have COP, we have Q hot, so we can get work net. So work net, so Q hot divided by COP heat pump is equal to COP heat pump. Okay, so here you need to convert into kilojoule per second. So 80,000 kilojoule per hour. Okay, times 1 hour 3,600 second. Okay, 3,600 second divided by 2.5. So you can get your answers in kilowatt. Okay, alright. Okay, so B, heat absorbed. Okay, so heat absorbed is your Q low. Okay, so work net is Q hot minus Q low. So we got all the figures. Okay, so Q low is Q hot minus work net. Alright, so Q hot we have, work net also have been calculated, so put in the value, so you got your answers here, kilowatt. Okay, alright, thank you. Reversible and irreversible process. When the system undergoes a change from its initial state to the final state, the system is said to have undergone a process. During the thermodynamic process, one or more of the properties of the system, like temperature or heat, pressure, volume, enthalpy, entropy, etc., change. The second law of thermodynamics enables us to classify all the processes under two main categories, which is reversible or ideal process and irreversible or natural process. So basically here we have two types. We call it as a reversible and irreversible. Normally reversible is ideal, which is in the theory. Okay, irreversible is normally is in nature. Okay, we look into reversible process. Reversible process, the process in which the system and surrounding can be restored to the initial state from the final state without producing any change in the thermodynamic properties of the universe. The reversible process can be reversed completely, and there is no trace left to show that the system had undergone thermodynamic change. There are two important conditions for the reversible process to occur. One, the process should occur infinitesimally small time. And two, all of the initial and final state of the system should be in equilibrium with each other. In actual practice, the reversible process never occurs. Thus, it is an ideal or hypothetical process. So we're interested in reversible process because number one, they are very easy to analyze, and number two, they serve as idealized, which is we have a limit. We call it as a theoretical limit to which actual process can be compared. Okay, so in order to determine using the actual process during calculation, we have many assumptions, many influence, many critical influence that govern the calculation. So basically, in order to easiest the calculation, we take an assumption for reversible process. Okay, irreversible process. The irreversible process is also called the natural process because all the processes occurring in nature are irreversible. The natural process occurs due to the finite gradient between the two states of the system. For instance, heat flow between two bodies occurs due to the temperature gradient, high and low, between the two bodies. This is, in fact, the natural flow of heat. Similarly, water flow from high level to low level, current move from high potential to low potential, and etc. In the irreversible process, the initial state of the system and surrounding cannot be restored from the final state. During the irreversible process, the various states of the system on the path of change from initial state to final state are not in equilibrium with each other. And during the irreversible process, the entropy of the system increases decisively, and it cannot be reduced back to its initial value. So the phenomenon of a system undergoing irreversible process is called as irreversibility. What is meant by irreversibility? It is the factor that cause a process to be irreversible. The irreversibility includes friction, unrestrained expansion, mixing of two fluids, heat transfer across a finite temperature difference, electrical resistance, inelastic deformation of solids, and chemical reaction. Internally and externally reversible process. Internally reversible process. If no irreversibility occur within the boundaries of the system during the process. So for external reversible process, no irreversibility occur outside the system boundary. So the total reversible process it involves no irreversibility within the system or its surroundings. So basically, a totally reversible process involves no heat transfer through a finite temperature difference, no non-quasi equilibrium change, and no friction or other dissipative effect. So basically, for no irreversibility inside the system, you got no irreversibility outside the system. Okay, so this is our assumption for reversible process. Carnot cycle. Carnot cycle is an ideal reversible closed thermodynamic cycle in which the working substance goes through the 4 successive operations of isothermal expansion to a desired point. Adiabatic expansion to a desired point, isothermal compression, and adiabatic compression back to its initial state. So this is the process. Process 1 to 2. Energy source. Energy being put into the process from initially to process 2, and then in the expansion. So in this process, we call it as the adiabatic expansion, and we assume it's being insulated and adiabatically, which means no heat being transferred outside. Okay, and then for process 4 to 3, 3 to 4 is a isothermal compression. 3 to 4, sorry, this is 3 to 4. 4 to 1. Okay, 3 to 4 is the isothermal expansion. Compression. Isothermal compression. Okay, reversible isothermal compression. And lastly, we have expansion. Okay, so this is, we call it as a isothermal expansion, whereby your temperature will be constant. So this 4 is a Carnot cycle. Okay, whereby we have 1, 2 isothermal, 2, 3 adiabatic, 2, 3 adiabatic, 3, 4 isothermal compression, and lastly adiabatic compression. Okay. So the reverse Carnot cycle. The Carnot heat engine cycle is totally reversible process. So therefore, all the process that comprise it can be reversed, in which case it becomes the Carnot refrigeration cycle. So basically, the Carnot cycle is ideal. In hypothetically, it can be done, but in reality, it cannot be done. Okay, but it gives basic assumption on what is needed, what is the calculation needed in order to construct the actual device. So if we consider the PV diagram, so this is, we call it as a Carnot cycle, normal Carnot cycle, 1 to 2 heat, process 1 to 2 heat being injected, 2 to 3 expansion from higher pressure to lower pressure, and 3 to 4, okay, heat being rejected, and now number 4 is compress again. Okay, compress again, higher temperature, higher pressure and much lower volume. So this is your 4 volume, this is your 1 volume. So compared to reverse Carnot cycle, so whereby 1, 2 is an expansion, heat being supplied, 2 to 3, 3 to 4 compress again, and 4 to 1 heat being rejected. Okay, the Carnot principle. The efficiency of an irreversible heat engine is always less than the efficiency of a reversible one operating between the same two reservoirs. The efficiency of all reversible heat engine operating between the same two reservoirs are the same. Okay, so basically, irreversibility, you don't have the same efficiency. But for reversible, the efficiency is the same. But you have the same reservoir. Okay, so that is the Carnot principle. Okay, the thermodynamic temperature scale. A temperature scale that is independent of the properties of a substance that are used to measure temperature is called a thermodynamic temperature scale. Such a temperature scale offers great convenience in thermodynamics calculation. Okay, so from here we call it as a Kelvin scale. Okay, and the temperature of this scale are called absolute temperature. Kelvin is minus 273. So you got your Q, heat being supplied to heat lower, is equal to temperature hot per temperature low. But it's in reversible process. If it's irreversible, you cannot have this equation. You cannot use thermodynamic temperature scale. So this is valid for reversible process. The Carnot heat engine. The thermal efficiency can be calculated as efficiency any heat engine. We got 1 minus Q low over Q hot, whereby Carnot heat engine 1 minus temperature low divided by temperature hot. So this is your thermodynamic temperature scale. Okay, so if your efficiency is less than efficiency of reversible, we call it as a irreversible heat engine. If your efficiency is the same with efficiency for any reversible engine, we call it as a reversible engine. If you got efficiency more than efficiency of reversible, impossible. Okay, so impossible heat engine. So which means that no, in nature, in actual, no efficiency is more than the reversible process. Sample problem 4.6. Sample problem 4.6. A Carnot heat engine receives 500 kJ of heat per cycle from a high temperature heat reservoir at 652 degrees Celsius and reject heat to a low temperature heat reservoir at 30 degrees Celsius. Determine A. The thermal efficiency of this Carnot engine, and B. The amount of heat rejected to the low temperature heat reservoir. Okay, so 4.6. So we have a higher condition at T high at 652 degrees Celsius goes to your pump. Okay, so you got your work net. Okay, so this is your low. Your low is T low is how much? 30 degree Celsius. Okay. Okay. So your Q hot is given directly 500 kilojoule. Okay. Okay. Alright. So A. Thermal efficiency. efficiency. Okay, so efficiency of Carnot cycle, Carnot, and it's a reversible, 1 minus T hot divided by T low. Okay, so this is your T hot, T low. Okay, so here be remind is in Kelvin. Okay, so 1 minus 652 plus 273 plus 30 plus 273. Okay, so you can get your efficiency. So sorry, this is Kelvin, this Kelvin. So unitless, efficiency is unitless. Okay, B, heat rejected to the low temperature. Heat rejected, which is your Q low. Okay, QL. Right, so the ratio of higher temperature to lower temperature is also similar with higher heat per lower heat per higher heat is similar with temperature higher divided by temperature temperature low at temperature high. Okay, so rearrange the equation. You got temperature low, okay, 30 plus 273 per, this is Kelvin. Temperature low is 652 plus 273 Kelvin times Q hot is 500 kilojoule. 500 kilojoule. Okay, so you got answer in kilojoule. Okay, right, thank you. The quality of energy. How do we increase the thermal efficiency of a Carnot heat engine? How about for actual heat engines? That is the question normally we ask in order we dealing with Carnot engine. So for this efficiency, we got efficiency for reversible engine, 1 minus temperature high, okay, divided by temperature temperature low divided by temperature high. So which means that if your temperature low is near to temperature high, we got 1. 1 minus 1 is 0. So which means that your efficiency is 0. So here we mean that in order to have a higher efficiency, this must be lower as possible, because here we got a efficiency which 1 is the greatest. So this portion you must lower as possible. Okay, so which means that something divided by infinity, you got infinity, but here you got value near to 0 in order to got your efficiency is higher to 100%. Okay, the question is, can we use Celsius unit for temperature here? Can we use it? The answer is we cannot, because we are in the thermodynamic temperature scale. So be aware for temperature, because we use in Kelvin scale. So please convert your Celsius into Kelvin. Carnot refrigerator and heat pump. The COP, coefficient of performance of a reversible refrigerator or heat pump, is the maximum theoretical value for the specified temperature limits. Actual refrigerator or heat pumps may approach this value as their design are approved, but they can never reach them. The COP of both of the refrigerator and heat pump decrease as your temperature low decrease. That is, it's required more work to absorb heat from lower temperature media. So in general, for any refrigerator or heat pump, your COP, we will use this equation. For a reversible, Carnot reversible refrigerator or heat pump, we can use temperature. Compared to any, as mentioned, it's not a Carnot, we use a heat supply. So be careful when you have a question. Either the question give you to calculate Carnot or any refrigerator or heat pump with no Carnot cycle. Okay. Sample problem 4.7. Okay. Sample problem 4.7. An inventor claims to have developed a refrigerator that maintains the refrigerated space at 2 degrees Celsius while operating in a room where the temperature is 25 degrees Celsius and has a COP, coefficient of performance, of 13.5. Is there any truth to his claim? Okay, so 4.7. Okay. Alright, so given in this example is hot is 25 degrees Celsius. Okay, so this is your QO hot, this is your heat engine. So hot work in is your work night. Okay, and this is your Q low, so this is your refrigerator. Okay, so temperature low is 2 degrees Celsius. Okay, so the COP claim is 13.5. So we need to calculate the COP. Okay, so COP. This is a refrigerator. Okay, so we have 1 per T hot per T low minus 1. Okay, do remember that this is in Kelvin. So Kelvin. Okay, so we got 1 over T hot. T hot is 25 plus 273 divided by 2 plus 273 K minus 1. So okay, take down the calculator, can know. Okay, so this is a unitless. Alright, so this figure compare with the claim of 13.5. So you can compare either it truth or not. Okay. Alright, thank you. Sample problem 4.8. Okay, sample problem 4.8. A heat pump is to be used to heat a house during the winter. The house is to be maintained at 21 degrees Celsius at all times. The house is estimated to be losing heat at a rate of 135,000 kilojoule per hour when the outside temperature drops to -5 degrees Celsius. Determine the minimum power required to drive this heat pump. Okay, so 4.8. Okay, so we have your desired is at 21. So T hot is 21 degrees Celsius. So this is your required Q hot. This is your pump. Then it be supplied work in, work net in. Okay. So this is your Q low. Okay. So T low is minus 5 degrees Celsius. Okay. So the losing heat. Okay, so from here, the losing heat to maintain the house at 21 degrees Celsius from minus 5 degrees Celsius is your heat required, heat being supplied. So the heat must be maintained at 135,000 kilojoule per hour. Okay, so here you need to convert into kilojoule per second or kilowatt. Okay, all right. So from here, power required, minimum power. So you need to determine your work net. What is the work net? Okay, so COP, heat pump, is equal to heat required over work net. Okay, so we have given directly the heat pump. We also have we don't know the work net. This is what we want to find, but we don't know the COP. So let us calculate first the COP. COP, heat pump in a reversible. So we got 1 over 1 minus T low over T high. Okay, so bear in mind this is in Kelvin. Okay, so 1 minus T low. Low is at minus 5 plus 273 divided by 21 plus 273. This is Kelvin. Okay, so you got your answers. Okay, all right. And also from this, you can, from this COP, you can substitute into this equation. So you got your work net is, okay, Q hot, so 135,000 kilojoule per hour. 1 hour 3600 second. Okay, in order to get kilowatt. Okay, divided by this value COP. Okay, COP put in below. So you got your work net kilowatt. Okay, all right, thank you.